Hello everyone, my name is Gonçalo Araújo and I'm presenting Integrating Algorithmic Processes in Informal Urban and Architectural Planning. As urban development is steadily increasing, it is estimated that by 2050, 66% of the world population will live in cities, from which 90% is predicted to be concentrated in Africa and Asia. This suggests an urbanization growth in many underdeveloped countries, highlighting the concern over the way informal housing fits in the economic, health, and climatic goals of these countries. The research here presented proposes the integration of algorithmic processes in urban and architectural planning, bridging a less explored frontier of design towards the age of post-carbon cities. Thus, we propose a three-phased workflow to structure data gathering, algorithmic processes, and analysis of a case study. The first phase comprises the definition of a case study's urban fabric and its respective building typology and climate data. Phase 2 includes the integration of model generation with performance simulations. By algorithmically modeling and using the specified urban area from OpenStreetMap data, local materials, and weather files as inputs, it is possible to estimate the impact on people's comfort and construction or rehabilitation costs. The selected case study is Xamanculo-C, a neighborhood in the city of Maputo, district of Inhamanculo. It is mainly populated by basic and densely distributed infrastructures in non-delimited areas that show high population density with very narrow public spaces. We use the OSM data to generate a 3D model of the corresponding houses that match the urban landscape, covering a total of 334 building units with 5 possible wall solutions and 2 possible roofs. Regarding the architectural planning analysis, one of the most common self-made houses seen in the area is the Ventuinha house. Landowners add units incrementally according to the family needs and their financial availability. These units usually have the same dimensions and are rotated so that the roof angles create a fan-like shape. To define the parametric model, we started from one cuboid unit joined with a triangular prism, with variable length, width, and height. To form a complete house, the starting unit is then rotated 4 times. To measure thermal comfort, the simulations were made for the summer period from 10 to 20, and outputs yield the percentage of time in which each house is in the comfort zone of the ASHRAE adaptive chart, a metric known as thermal autonomy, or TA. Construction scenario 1 and 2 represent the original scenarios in the area, full zinc houses and cement walls with zinc roofs. Both showed similar low levels of thermal autonomy between 30 and 40%. Scenario 3 and Scenario 4 respectively have a double pane of zinc walls and cement with zinc roofs. Scenario 3 shows levels of thermal autonomy between 27 and 43% with an average of 34, while Scenario 4 shows levels of thermal autonomy between 33 and 69% with an average of 44. Finally, Scenario 5 encompasses the same roof and a combination of a zinc and cement layer as walls, and show values between 29 and 54% with an average of 38. By changing the roof construction of these scenarios to a double zinc cladding with insulation, a wider look shows that the same wall scenarios with this second roof show greater improvements in every construction. Consequently, regardless of the wall construction, a roof upgrade emerges as the most viable option of slum upgrade. Moreover, houses in different areas of the neighborhood vary their TA according to both their surface area and their context and surroundings. Thus, it is possible to define different rehabilitation plans for critical areas that have bigger upgrades of TA variation from the original scenarios. This figure shows the results of the TA variation on a scale from 0% or below in red to 100% and above in green. The performance of the wall scenarios is clearly dependent on the roof construction, which acts as a catalyst for comfort improvement. This is illustrated by scenarios 4 and 5, which provide little to no improvements with roof 1 and the best performing solutions with roof 2. However, Many buildings have significant TA increases with less costly walls and or roof rehabilitation scenarios. The wide range of viable design solutions and corresponding impact factors can be difficult and time-consuming to analyze and control, highlighting the need for optimization process. In this case, optimization process would be applied regarding costs and TA improvements of the whole urban model. If we compare the respective cost of rehabilitation of each building with each scenario, it is possible to grasp that the original with only a roof upgrade would cost as much as rehabilitating with any better wall scenario, while yielding similar and in some cases even better results. Additionally, this comparison reflects the conflicting nature between TA and costs. However, with the integration of optimization processes, it might be possible to determine a good solution with lower costs by applying higher cost materials only in critical buildings according to comfort results. Regarding the Ventoinha house dimensions, the simulated model comprises a single house with scenario 5 and roof 2, and an acceptable range of height and unit surface area. Results show a decrease of up to 4% as the height increases, and an improvement of 4 up to 7% as the area increases. If we now compare all scenarios with roof 2 and higher surface areas, TA increases in larger proportional areas, and scenario 2 proves to perform better than 1 and 3 in areas up to 100 square meters. However, the TA of scenario 3 is similar to the one of scenario 2 above those limits. Two scenarios easily stand out as better construction solutions regarding the impact of surface area, showing larger TA and less amplitude. In conclusion, we present a methodology capable of integrating algorithmic processes in both urban and architectural planning. With low resources and in a time-efficient way, this methodology can yield valuable insights regarding the impact in thermal comfort, materials, costs, and design dimensions. Future work will explore the integration of optimization processes in this methodology regarding other comfort metrics such as visual, thermal, and airflow, to provide fair and low-cost solutions for informal housing rehabilitation and planning. Thank you all for watching. Have a nice day.